Good morning, everyone. My name is Shichang Zhu. I'm a fourth-year PhD student from SYE at Georgia Tech. I'm glad to be here today to present our recent work on sequential adversarial anomaly detection for dependent events. This is a joint work between two other students in our group, Henry and Minghe, and my advisor, Dr. Yao Xie. Event data are very common in our daily lives. Some examples include seismic activity record, police report, electronic transaction record, and network package data. Event data usually consist of a sequence of discrete events that indicate when and where each event occurred, as well as other additional information such as its category or volume. In many scenarios, when the anomalous event occurs, it may be followed by a series of abnormal events. In the context of seismic activities, it may refer to major earthquake and its subsequent aftershocks. For police reports, it may correspond to a series of connected crimes, and so on. In other words, these anomalies do not happen on its own, but triggers each other. Preventing these events from happening are crucial to our public safety or avoid further economic losses for societal benefits. Our goal here is to detect a sequence of anomalous events as quickly as possible in a real-time fashion. A motivating example is credit card fraud detection at department store. As demonstrated in the figure, the events in this setting correspond to a sequence of unauthorized credit card transactions. Each transaction record typically includes information on time, location, and transaction amount of the purchase. For example, Mr. Simpson woke up at 5:30 in the morning. He felt particularly good, so he broke into his neighbor Mr. Flanders' house and stole his credit card. Then he drove downtown for the sunrise. He got into McDonald's at 6 for a full breakfast. And then he planned to go on a shopping spree at Macy's, and so on. Now, the challenge would be to try and stop Mr. Simpson from this madness as soon as possible. If we are the expert on the right-hand side, we may easily identify these purchases as fraudulent based on the pattern of these activities, which is supposed to be dramatically different from Mr. Flanders' transaction pattern and spending habit. Again, the idea is to identify this anomalous pattern not only accurately, but also efficiently. Now, let's look at some real credit card fraud cases provided by Macy's department store, which is one of the real examples that we have been working on. For the first figure on the left, it shows a fraudster used a stolen card for 12 times in the time span of 6 days. X-axis represents time and the Y-axis represents transaction amount, and the color code indicates the location where these purchases are made. And you can see that these transactions were made at stores far away from each other, ranging from California to New England. And we also have additional information for these records, such as the type of transaction, for example, whether the card is used physically in store or it is used online. Overall, this spatial temporal dynamics may also be quite different from the normal spending pattern of the card. The second figure on the right illustrates a collection of a larger number of fraudulent transactions. We can see that a significant portion of transactions occurred solely at Macy's Herald Square and the Macy's Union Square, which are two largest department stores in the US. It is noteworthy that such spatial temporal dynamics of credit card transactions are not commonly seen amongst ordinary purchases. So now we can understand to stop frauds and prevent further losses for both consumers and retailers, identifying whether a sequence is an anomaly as soon as possible is really an urgent need for both sides. And we also want to point out a lot of agencies or entities like Macy's cannot provide normal data for various reasons. Particularly, Macy's is unable to provide normal transactions from customers just to protect consumers' privacy, which literally creates a situation where only anomalous transaction data are available. Here, we summarize 3 major challenges in our problem setting. First of all, there are only one class anomalous data available, which requires an unsupervised approach for anomaly detection. Secondly, many existing works consider detecting anomalous sequences as a single data point rather than detecting in the online fashion, which means detection can be made until the sequence has been fully observed. This makes most of these methods cannot be directly applied here. Last but not least, how to carry out detection in a computationally efficient way is also one of the major concerns when we are implementing our algorithm in practice. As you can see, if the sequence is too long or the data tuple of each event is a high-dimensional vector, carrying out stepwise detection would be computationally inefficient. Now we focus on the problem where only anomalous sequences are available. We aim to develop a detector that can detect anomalous sequence in a real-time fashion and raise the alarm as soon as possible. Formally, assume a sequence with n event is observed. We denote its first I element as x1 to I. The detector actually is a stopping rule. At each time t, it evaluates a statistic and compares it with a threshold. The detection will stop and raise alarm the first time that the detection statistic italic L exceeds the threshold eta I. Here, the italic L refers to our anomaly detector, which returns the detection statistic given the partial observation. And eta I is the time variance threshold, which means the threshold that triggers alarm will be changing over the time. To meet this challenge, we propose a robust and unsupervised sequential anomaly detector via adversarial learning. In addition to an anomaly detector italic L specified by theta, we introduce an adversarial generator since normal data are not available. The generator produces normal sequences that are statistically similar to real anomalies. The detector aims to discriminate the true anomalies from such counterfeits. Meanwhile, the generator is trying to generate fake anomalies without detection. The competition between the anomaly detector and the generator drives both models to improve their performance until anomalies can be always distinguishable from counterfeits in the worst case scenario. Formally, we assume the observed anomalous sequence X are sampled from empirical distribution pi. The counterfeit sequence Z are sampled by an adversarial generator specified phi. The problem can be defined as the following minimax optimization problem. The first term corresponds to the expected detection statistic of anomalies, and the second terms correspond to the same statistic of the counterfeits. The inside of the minimax, which is the function j, measures the discrepancy of such expected detection statistics between genuine anomalies and counterfeits. Now we define the following adversarial anomaly detector. Since, as we mentioned, the value of the detection function italic L for sequence x1 to I may vary over time step I, we need to adjust the threshold accordingly for making decisions as a function of I. Now, if we denote the pair of solutions to be the minimax problem we showed in the last slide as theta star and phi star, which refers to the optimal detector and optimal generators respectively, if the detection statistic given the optimal detector theta star is larger than an optimal time variance threshold eta I star, then the sequential adversarial detector raises alarm at time step I. Note that optimal time variance threshold eta I star is proportional to the expected detection statistic of counterfeits generated by the optimal generator. The statistic can also be approximated empirically by generating a number of fake sequences using the optimal generator phi star and take the average. As we all know, a notorious difficulty in evaluating the likelihood function for Hawkes process, which requires calculating the integral of lambda over the spatial temporal space. It could be computationally intractable if the space is multidimensional. Now we define our model in a similar way as follows. First, mu is still the constant background intensity of the events, which can be estimated from the data. The alpha represents the magnitude of the influence from the past, and most importantly, a deep Fourier kernel function measures the influence of the past event x prime on the current event x. Specifically, the deep Fourier kernel is defined as the inner product between x and x prime's Fourier embeddings. The Fourier embedding phi x can be viewed as the approximation of the kernel-induced feature mapping, which consists of a number of Fourier features from the optimal spectrum specified the distribution p omega. The optimal spectrum is represented by a deep neural network. The input of the network is a Gaussian noise prior. and the output is the Fourier feature sample from the spectrum. As shown in this illustration, the process of evaluating kernel at x and x prime is analogous to performing inverse Fourier transform of the optimal spectrum. The parameter of the Fourier feature generator will be trained along with other parameters in the model through maximizing log likelihood function. Most importantly, as we mentioned before, the detection needs to evaluate the log likelihood function at every time step, which requires computing the integral of intensity function over multidimensional marked spatial temporal space. In many existing works, this thing is carried out by some numerical integration techniques. In our setting, this step could be computationally intractable if the structure of the intensity function is not carefully crafted. Now, by taking advantage of the form of the Fourier kernel, the integral can be carried out in a closed form. Now, let's look at the parameterization of our adversarial sequence generator, which will be used in generating counterfeit sequences and calculating time variance threshold. To achieve rich representation power for the adversarial generator GZ, we borrowed the idea of a recurrent neural network structure. First, the output of each step is sampled from the Gaussian distribution, where the parameter of distribution is specified the current hidden state. Second, the hidden state is not only dependent on the last state, but also dependent on the last output. In the experimental section, we performed comprehensive numerical studies on both synthetic and real data sets to compare the performance of a proposed adversarial anomaly detector with the state of the art. It confirms that the proposed time variance threshold can optimally separate the anomalies from the normal sequences. To be specific, the fourth column shows the average log likelihood and its corresponding 1 sigma region for both anomalies and normal sequences. As we can see, the anomalous sequence attain a higher average log likelihood than the normal sequences for both datasets. Their log likelihood falls into different value ranges with rare overlap. Additionally, the time variance threshold indicated by blue dashed line lies between the value ranges of anomalous and normal sequences, which produce a nice separation of these two types of sequence at any given time. The first three columns present more compelling evidence that the time variance threshold is near optimum. The brightest region indicate the ground truth of the optimal choice of the threshold. As shown in the third column, the time variance threshold, which is the blue dashed line, are very close to the optimal choices found by the cross-validation. For the Macy's fraudulent credit transaction data, we can also draw the similar conclusion from the experimental result as well. We also compare the stepwise F1 scores with the other 4 baselines, including one-class SVM, PCA Q-sum, local outlier factor, which all are the state of art in the anomaly detection, as well as the recent study on taking advantage of inverse reinforcement learning to attack sequential anomaly detection problem. Result has shown that first, from the overall standpoint, our method outperforms other baselines with significantly higher F1 scores. And second, our method allows for easier and faster detection of anomalous sequences, which is critically important in sequential scenario for most of the applications. Now, as a summary, we have presented a novel unsupervised anomaly detection framework on sequential data based on adversarial learning. We also proposed a robust detector which can be found by solving a minimax problem, and the optimal generator can also help in defining the time variance threshold for making decisions in an online fashion. In addition, we modeled the sequential event data using the marked point process model with a deep Fourier kernel. Using both synthetic and real data, we demonstrate that our proposed approach outperforms other state-of-the-art. We believe the proposed framework is a natural way to tackle the one-class anomaly detection problem by taking advantage of the adversarial learning. This new formulation may provide a first step towards bridging imitation learning and sequential anomaly detection. Thank you very much for your attention.